Look up at the night sky, and what do you see? Darkness, yes, but also pinpricks of light, scattered like diamonds on black velvet. For centuries, humans have gazed at those stars and wondered, is there anything in the vast emptiness between them? The answer is far more extraordinary than we ever imagined. The universe isn't a barren void. It's alive with structure, a hidden architecture that binds everything together. This is the cosmic web, an invisible network of gas, dark matter, and galaxies that stretches across the cosmos like the threads of a spider's silk. And it's not just out there, it shapes everything, from the birth of stars to the fate of the universe itself. Think of it like this. If the universe were a city, the cosmic web would be its streets and highways, guiding the flow of matter and energy. Without it, galaxies would drift apart, stars would never form, and the universe as we know it wouldn't exist. But how did we discover this hidden framework? And what does it tell us about our place in the cosmos? The story begins with ancient astronomers who mapped the heavens, evolves through groundbreaking telescopes that peer into the depths of space, and leads us to today's most advanced simulations, revealing a universe more interconnected than we ever dreamed. This isn't just a tale for scientists. It's a story about curiosity, about humanity's relentless drive to uncover the secrets of the cosmos. Because understanding the cosmic web doesn't just explain where galaxies come from, it helps us see the universe as a living, breathing entity, one that we're all a part of. So let's journey together from the first glimpses of this hidden structure to the mind-bending discoveries that are rewriting our cosmic story. By the end, you'll never look at the night sky the same way again. To grasp just how vast and intricate the cosmic web really is, picture standing in front of the world's most complex tapestry, one woven not with threads, but with galaxies. Each strand of this web is a filament of gas and dark matter, stretching millions of light years across the universe, with galaxies clustered at the intersections like glittering jewels. These filaments aren't just cosmic decoration, they're the scaffolding of existence, the framework upon which everything is built. The story of how we uncovered this hidden structure is as fascinating as the web itself. In the 1970s, astronomers mapping the positions of galaxies noticed something strange. Instead of being scattered randomly, galaxies seemed to gather in enormous clusters, separated by vast, empty voids. It was as if the universe had a blueprint, a pattern dictated by gravity, sculpted over billions of years. But confirming this theory required more than just observations. It took supercomputers running simulations of the universe's evolution, tracing how tiny ripples in the early cosmos grew into the sprawling cosmic web we see today. And what a revelation it was! Those simulations showed that dark matter, the invisible glue holding the universe together, forms an intricate web long before galaxies even exist. Ordinary matter, the stuff we're made of, simply flows along these dark matter highways, pooling where filaments intersect to ignite the birth of stars and galaxies. Without this underlying structure, the universe would be a formless sea of gas with no galaxies, no stars, and no planets like ours. But here's what's truly mind-bending: the cosmic web isn't static. It's alive with motion, constantly shifting as gravity pulls matter into denser knots and expansion stretches the voids wider. Galaxies ride these currents like ships on an invisible ocean, moving toward the web's densest regions over billions of years. Even now, our own Milky Way is being drawn toward the Great Attractor, a mysterious concentration of mass hidden behind the dust of our galaxy. What makes this discovery so extraordinary isn't just the scale of the cosmic web, it's how this hidden architecture connects everything. The same forces that shaped the web also shaped us, guiding the formation of the stars that forged the elements in our bodies. In a very real sense, we are children of the cosmic web, born from its structure and bound by its unseen threads. And as telescopes grow more powerful, revealing finer details of this grand design, we're not just mapping the universe, we're uncovering the story of our own origins. Dark matter is the unseen force holding the cosmic web together, an invisible architect shaping the universe from the shadows. Picture a massive construction site where workers have vanished, leaving behind only the steel framework of a skyscraper. That framework is dark matter, and the skyscraper is the universe we see. It doesn't emit light or interact with ordinary matter in any way we can detect, yet its gravitational pull is undeniable. Without it, galaxies would spin themselves apart, and the delicate filaments of the cosmic web would unravel like a sweater missing its threads. How do we know it's there? The clues are everywhere. Take spiral galaxies, for example. The stars at their outer edges orbit just as fast as those near the center, defying the laws of gravity as we understand them unless there's an invisible mass, a gravitational anchor keeping everything in place. Then there's the way light bends around galaxy clusters, warping like a funhouse mirror. This phenomenon, called gravitational lensing, reveals the presence of far more mass than we can see. Dark matter's fingerprints are all over the cosmos, even if we've never caught a direct glimpse. But here's where it gets even stranger. Dark matter isn't just hanging around passively, it's dynamic, clumping into dense knots under its own gravity. These knots act like cosmic traffic hubs, funneling ordinary matter, the gas that forms stars and planets, into the intersections of the web. Supercomputer simulations show this process unfolding over billions of years. Dark matter forms the skeleton first, and the visible universe slowly builds upon it. Without these invisible nodes, galaxies would never have gathered into clusters, and the cosmic web would be a ghost town. Yet for all its importance, dark matter remains one of the universe's greatest puzzles. Is it a particle, some undiscovered sibling to the protons and electrons we know? Or is it something even more exotic, a substance that bends the rules of physics as we understand them? Experiments deep underground, in abandoned mines and mountain tunnels, hunt for fleeting interactions between dark matter and ordinary atoms. Space telescopes map its distribution across the sky, tracing the outlines of its hidden empire. Every answer we find only deepens the mystery, revealing how much we still don't understand about the fabric of reality. What's clear is this: dark matter isn't just a curiosity. It's the foundation of everything, the cosmic web, the galaxies within it, even our own Milky Way. None of it would exist without this enigmatic substance. And as we peel back the layers of the universe, we're not just searching for dark matter. We're searching for the missing chapters of our own story, written in the invisible ink of gravity. Galaxies don't float through space alone. They gather where the cosmic web's filaments cross, forming bustling intersections of matter we call nodes. Imagine these nodes as grand central stations in an intergalactic transit system, where dozens of galaxies converge, drawn together by gravity's relentless pull. The Milky Way itself sits within one such node, part of the Laniakea supercluster, a sprawling family of over 100,000 galaxies spanning 500 million light-years. Yet even this vast structure is just one thread in the universe's greater tapestry. What makes these nodes so special? Density. Where filaments intersect, matter piles up like snowdrifts at a crossroads, creating environments ripe for galactic growth. Here, galaxies don't just passively coexist, they interact, sometimes merging in spectacular collisions that trigger bursts of new star formation. The Virgo cluster, our nearest galactic node, contains over 2,000 galaxies packed relatively close together, their gravity influencing one another's movements in an endless cosmic dance. Astronomers use these dense regions as signposts to trace the web's architecture. By measuring how galaxies move within nodes, we've discovered they aren't stationary. They flow along filaments like commuters following subway lines. The Milky Way, for instance, is being pulled toward the Great Attractor at over 600 kilometers per second, riding a filament toward one of the web's most massive junctions. This motion isn't random, it follows pathways carved by dark matter billions of years ago. The real magic happens when we zoom out to see nodes in context. From this perspective, superclusters resemble neurons in a cosmic brain, with filaments acting as axons transmitting matter between them. Simulations show these structures evolving over time, small nodes merging into larger ones, filaments strengthening as they accumulate more galaxies. Some nodes become so massive they distort space-time itself, bending light from objects behind them in a phenomenon called strong gravitational lensing. Yet for all their grandeur, these nodes are temporary waypoints in an ever-changing universe. As expansion accelerates, some filaments will stretch too thin to supply fresh matter, leaving once vibrant nodes to fade into isolation. Others will grow denser still, becoming the mega-cities of tomorrow's universe. By studying them now, we're capturing a snapshot of an unfolding story, one where gravity writes the plot, and galaxies are both actors and audience. The cosmic web's filaments aren't just invisible scaffolding, they're rivers of life, flowing with gas so hot and thin, it would barely register as a whisper in Earth's atmosphere. This intergalactic medium, mostly hydrogen and helium, is the raw material of creation itself. Picture it as the universe's bloodstream, coursing through dark matter's veins to deliver the ingredients for stars, planets, and even us. Some of this gas has remained untouched since the dawn of time, pristine relics of the Big Bang drifting in the voids between galaxies. Other regions glow faintly, energized by the intense radiation of quasars, supermassive black holes that act like cosmic lighthouses, ionizing the gas around them and revealing the web's hidden structure. How do we study something so diffuse? The answer lies in starlight. When light from distant quasars travels through the cosmic web, it passes through these gas filaments like sunlight filtering through stained glass. The gas absorbs specific wavelengths, leaving behind a fingerprint, a barcode of absorption lines that telescopes like Hubble can decode. These patterns tell us not just where the gas is, but how it moves, how hot it is, and even what elements it contains. It's as if the universe left us a trail of breadcrumbs written in ultraviolet and X-ray light. But this gas isn't just floating aimlessly. Gravity pulls it along the cosmic web's filaments, funneling it toward galaxies like water rushing into a drain. When enough gas accumulates, it collapses under its own weight, igniting the fires of newborn stars. Without this steady supply, galaxies would exhaust their fuel in a cosmic blink, leaving the universe dark and lifeless. The Milky Way, for instance, is still growing, siphoning gas from the surrounding web to forge new generations of stars. Yet not all gas reaches its destination. Some is stripped away by collisions between galaxy clusters, leaving behind glowing trails that stretch for millions of light years. Other gas clouds are so hot they resist collapsing, hovering in a state of suspended animation until gravity finally wins the tug-of-war. And in the deepest voids, gas remains so sparse it might never form stars at all, a relic of the universe's earliest moments frozen in time. What's astonishing is how much we've learned about this invisible ocean. By mapping its currents, we've uncovered the delicate balance that keeps galaxies alive. Too much gas and stars form in a frenzy, burning out quickly. Too little and galaxies wither. The cosmic web doesn't just connect galaxies, it sustains them, a silent partner in the dance of creation. And as new telescopes probe even deeper, we're beginning to see how this gas shapes not just individual galaxies, but the entire large-scale structure of the universe. From the tiniest wisp of hydrogen to the vast flows that span billions of light years, the intergalactic medium is the unsung hero of the cosmic story, the breath that gives the universe life. To understand how the cosmic web began, we need to rewind time, all the way back to the universe's first trillionth of a second. In that fleeting moment, the cosmos wasn't smooth and uniform. Instead, it crackled with quantum energy, tiny fluctuations so small you'd need a microscope 1 billion times more powerful than anything we have to see them. Yet these microscopic ripples held the blueprint for everything that followed. Like seeds scattered in soil, they would grow into galaxies, clusters, and the vast filaments we see today. The real magic happened during cosmic inflation, a period when the universe expanded faster than light itself. In less than the blink of an eye, those quantum wrinkles were stretched to cosmic proportions, frozen into the fabric of space-time as variations in density. When the Big Bang's fireball cooled enough for matter to form, gravity got to work. Over billions of years, it sculpted those subtle differences into the universe's grand design, pulling matter into dense knots where galaxies would bloom, leaving behind empty voids and spinning delicate threads between them. We can still see echoes of this process in the cosmic microwave background, the afterglow of the Big Bang. Satellite missions like Planck have mapped this ancient light with breathtaking precision, revealing a patchwork of hot and cold spots. Those patterns aren't random, they match the cosmic web structure perfectly. The slightly warmer regions, those are the seeds of future filaments, where extra density would one day pull in galaxies. The cooler spots, the birthplace of voids. It's as if the universe left us a photograph of its infancy, a snapshot of the cosmic web in its earliest stages. But the story doesn't end there. Dark energy, the mysterious force accelerating the universe's expansion, is now stretching the web in new ways. Filaments grow longer and thinner, while voids expand like bubbles in rising dough. Some simulations suggest that in the far future, the web may tear apart entirely, a sobering reminder that even the universe's largest structures are temporary. Yet for now, this fossilized imprint of the Big Bang remains our best window into the past, present, and future of the cosmos. What's astonishing is how much these ancient ripples still shape us. The same fluctuations that seeded galaxy clusters also determined where Earth would one day form. In a very real sense, we're the product of quantum randomness amplified across 14 billion years, a reminder that the universe's grandest designs often begin with the smallest whispers. To witness the cosmic web in action, we don't need a time machine, just the raw power of modern supercomputers. These technological marvels, like the ones humming away at NASA and CERN, perform a kind of digital alchemy. They take the known laws of physics, gravity, the behavior of dark matter, the expansion of the universe, and weave them into virtual universes, compressing billions of years of cosmic evolution into mere days. The results are breathtaking, intricate simulations that mirror the real universe with uncanny precision, revealing how delicate filaments twist, collide, and merge, seeding galaxies at their intersections like pearls strung along invisible threads. What makes these simulations so revolutionary is their predictive power. When astronomers compare these digital universes to actual telescope observations, the match is astonishing. The same patterns emerge, the same clustering of galaxies, the same vast voids, the same delicate bridges of matter spanning the emptiness. This isn't just a happy coincidence. It's a profound validation of our understanding of dark matter's role as the cosmic web's architect and gravity as its sculptor. Without these simulations, the web's complexity would remain locked in the realm of theory, a beautiful idea without proof. But simulating the universe isn't like rendering a movie. Every particle, every interaction must obey the laws of physics with perfect fidelity. Early attempts in the 1980s could barely handle a few thousand virtual galaxies. Today's models, running on machines with millions of processors, track trillions of particles, each representing a clump of dark matter or a pocket of gas. The resolution is so sharp that scientists can watch individual galaxies form in real time within the simulation, emerging from the web's dense knots like flowers blooming at the crossroads of invisible highways. Perhaps the most startling revelation from these simulations is how dynamic the cosmic web truly is. Filaments don't just sit idly, they writhe and snap like whips under gravity's pull, sometimes merging to form thicker superhighways. Galaxies are nudged along these currents, drawn into clusters where they'll eventually collide or merge. Even the voids play an active role, expanding like bubbles in boiling water, their emptiness shaping the web as much as the matter itself. Watching these simulations feels like peeling back the skin of the universe to reveal the pulsing, ever-shifting machinery beneath. As computing power grows, so does our window into the cosmic web's secrets. Next-generation simulations are beginning to incorporate new layers of complexity. The turbulent feedback of supernova, the fierce winds blown by supermassive black holes, even the subtle influence of dark energies accelerating push. These virtual universes are no longer just models. They're testing grounds for ideas about how galaxies form, why they cluster where they do, and what fate awaits the web itself as dark energy stretches it ever thinner. Yet for all their sophistication, these simulations still leave mysteries unsolved. Why do some filaments seem brighter with gas than others? How do the smallest galaxies survive the violent tides of cluster formation? Each question drives scientists to refine their models further, pushing hardware and software to their limits in pursuit of a deeper truth. What's clear is that these digital cosmos have become indispensable, not just as tools for discovery, but as bridges between the abstract equations of physics and the tangible universe we see when we look up. They remind us that the night sky isn't just a scattering of stars, it's a living, evolving network, and we're just beginning to trace its threads. Modern telescopes have become our eyes into the invisible, revealing the cosmic web's hidden architecture in ways that would astonish early astronomers. The James Webb Space Telescope, with its infrared vision, peers through cosmic dust to catch the faint glow of gas filaments, threads so dim they're 1,000,000 times fainter than the night sky. It's like trying to spot a single candle flame on the moon from Earth, yet these observations are rewriting our understanding of how matter flows between galaxies. But JWST isn't working alone. Ground-based projects like the Sloan Digital Sky Survey have spent decades mapping the positions of millions of galaxies, painstakingly reconstructing the web's three-dimensional skeleton. Imagine plotting every city, town, and village on Earth to reveal the underlying geography. That's what astronomers are doing on a cosmic scale. The result: a sprawling atlas of the universe where galaxies cluster along filaments like beads on a string, separated by voids so vast they could swallow thousands of Milky Ways. Quasars, the brilliant cores of distant galaxies, serve as cosmic lighthouses in this endeavor. As their light journeys billions of years to reach us, it passes through the web's gas filaments, absorbing specific wavelengths. By decoding these absorption lines like reading the stains left by coffee passing through a filter, scientists measure the composition, temperature, and even the motion of the intergalactic medium. Some of this gas is pristine, unchanged since the Big Bang, while other regions bear the chemical fingerprints of generations of exploded stars. The most astonishing breakthroughs come when we combine these tools. JWST detailed snapshots of gas clouds align perfectly with Sloan's galaxy maps, confirming that filaments funnel matter directly into star-forming regions. It's as if we've found the universe's hidden plumbing system, watching the pipes that feed galaxies their lifeblood. Even empty voids play a role. Their sheer size creates pressure differentials that subtly steer gas flows, like atmospheric currents shaping weather patterns. Yet for all this progress, mysteries remain. Some filaments glow brighter than expected, hinting at unknown energy sources. Others appear oddly twisted, as if tangled by invisible hands. With each new observation, the cosmic web grows more complex, not just a static scaffold, but a dynamic, evolving entity. Upcoming instruments like the extremely large telescope will peer even deeper, probing the web's finest threads and perhaps uncovering new physics hidden in their patterns. What's clear is this: the universe's emptiness was always an illusion. Behind the darkness lies an intricate network, a living lattice of matter and energy that connects every galaxy, star, and planet. And as our telescopes grow sharper, they're not just mapping the cosmos, they're revealing our place within its grand design. Venture into the deepest reaches of the cosmic web, and you'll find something even more astonishing than its glittering filaments, the voids. These aren't just empty spaces, they're staggering in scale, some so vast they could swallow thousands of Milky Way galaxies with room to spare. Picture standing in the middle of an empty football stadium, except this stadium stretches for hundreds of millions of light years. Its bleachers made of distant galaxy clusters, its field an eerie nothingness where matter is so sparse you'd struggle to find a single atom in a space the size of your living room. Yet calling these regions empty is misleading. They're more like cosmic deserts, parched landscapes where gas is thinner than the best vacuum we can create on Earth, and dark matter drifts like faint shadows. Even here, the universe whispers its secrets. The gas in voids isn't just absent, it's been pushed out over billions of years, squeezed by gravity into the web's filaments like water fleeing a sponge. This evacuation leaves behind a fossil record, a subtle imprint of how the cosmic web grew and shifted, with voids acting as negative space sculptures carved by the universe's expansion. What makes voids so valuable to astronomers isn't what they contain, but what they don't. Their emptiness acts as a control group for the universe, a baseline to measure how densely packed regions behave. When we compare galaxies near voids to those in crowded filaments, we see gravity's handiwork in stark relief. Void galaxies, isolated and starved of raw material, often look anemic, small, faint, and aging quietly. Their cousins in dense clusters, bathed in flowing gas, blaze with newborn stars. It's as if the cosmic web is a vast ecosystem, with galaxies evolving differently depending on their zip code. But voids aren't passive bystanders. Their sheer size shapes the web's very architecture. As the universe expands, these empty regions grow faster than their surroundings, their lack of gravitational pull allowing space itself to stretch more freely. This creates pressure differences that subtly steer gas flows, like atmospheric highs and lows guiding weather systems. Some simulations even suggest voids may act as cosmic pumps, their expansion sucking matter outward and feeding the filaments that cradle galaxies. The most fascinating voids defy expectations. Some, like the Boötes void discovered in the 1980s, are so conspicuously empty they've earned nicknames like the Great Nothing. Stretching 300 million light-years across, it contains only a handful of galaxies where thousands should exist, an anomaly that still puzzles astronomers. Others show faint traces of warm gas, glowing at temperatures of millions of degrees, likely heated by ancient shockwaves from long-ago collisions between galaxy clusters. Studying these voids is like reading the universe's diary in reverse. Their sizes and distributions encode information about dark energy's push, the nature of dark matter, even the physics of the early universe. By mapping their shapes, some spherical, others elongated like stretched taffy, we can trace how gravity and expansion have battled across cosmic time. Upcoming telescopes like the Vera Rubin Observatory will scan thousands more voids, turning these cosmic absences into some of our most powerful tools for understanding the everything around them. Perhaps the most poetic truth about voids is this: without them, the cosmic web couldn't exist. Their emptiness defines the web's structure as much as the filaments themselves, creating the contrast that makes the universe's architecture visible. They remind us that absence can be as meaningful as presence, that in the grand tapestry of the cosmos, even nothingness tells a story. Imagine a galaxy as a city, a bustling metropolis of stars, planets, and cosmic activity. But just like any city, it needs resources to grow. Enter the cosmic web, the universe's ultimate supply chain. Those delicate filaments threading through the cosmos aren't just decorative. They're lifelines, pumping gas into galaxies like arteries delivering oxygen to a living organism. Without this steady influx of raw material, galaxies would starve, their star-forming factories grinding to a halt. Take the Milky Way. Right now, it's sipping from a filament of gas flowing in from the Intergalactic Medium, a process astronomers call cold accretion. This isn't some violent cosmic waterfall. It's a gentle, persistent drizzle of hydrogen and helium, just dense enough to collapse under gravity and ignite new stars. But the web doesn't just feed galaxies, it shapes their very destiny. Where filaments intersect, galaxies cluster like commuters at a transit hub, pulled into each other's gravitational embrace. Some merge in spectacular collisions, their gas clouds crashing together in bursts of star formation so intense they outshine entire galaxies. Others, stripped of their gas by these encounters, become red and dead, ellipticals aging giants with little fuel left for new stars. Even black holes owe their growth to the web. Supermassive ones lurking in galactic centers feast on gas funneled along filaments, flaring into quasars so bright they outshine their host galaxies. When two galaxies merge, their black holes spiral together, sending ripples through space-time as gravitational waves. These cosmic events aren't random, they're choreographed by the web's invisible architecture, with filaments directing the flow of matter like celestial traffic signals. The proof is in the patterns. Look at spiral galaxies, their graceful arms trace the whirlpool motion of gas spinning in from the web. Dwarf galaxies, those tiny cosmic backwaters, often cling to filaments like pearls on a string, their formation stunted by the limited supply of gas in their isolated locations. Even the Milky Way's satellite galaxies, like the Large Magellanic Cloud, are likely prisoners of a filament, caught in our galaxy's gravitational pull as they ride the same cosmic current. What's breathtaking is how long this process takes. A single filament might nourish a galaxy for billions of years, a slow-motion umbilical cord feeding generations of stars. Yet the web is also ruthless. Galaxies that stray into voids, cut off from these supply lines, slowly fade into obscurity. Their gas reserves deplete, star formation sputters out, and they become cosmic ghost towns. This intricate dance of creation and destruction reveals the web's true nature. It's not just a stage for galaxies, but the director of their evolution. From the tiniest dwarf galaxy to the largest cluster, Every structure owes its existence to this vast, interconnected network. And as we peer deeper into the universe's history, we're finding that the earliest galaxies formed precisely where the web's filaments first took shape, proof that the cosmos has always been a place of connection, not emptiness. The cosmic web doesn't exist in isolation. It's locked in a silent, cosmic tug-of-war with one of the universe's most mysterious forces, dark energy. Picture this immense structure as a vast network of rubber bands, each filament pulled taut by gravity's grip, while dark energy stretches space itself like an invisible hand yanking at the fabric of reality. For billions of years, gravity has been the dominant architect, sculpting galaxies and weaving filaments into the web's intricate design. But dark energy is the wild card, an enigmatic force causing the universe to expand faster and faster, diluting the very matter that holds the cosmic web together. Here's the paradox: the more the universe expands, the stronger dark energy's influence becomes. Think of it like a snowball rolling downhill, except instead of snow, it's empty space accumulating, pushing galaxies apart with relentless efficiency. Filaments, once robust highways of gas and galaxies, grow thinner over time, their material spread across ever greater distances. Voids, already vast, balloon outward, their emptiness swallowing the delicate threads that connect the web's remaining knots. The result, a universe where gravity struggles to keep up, where the cosmic web's once vibrant structure frays at the edges. We're already seeing hints of this battle in action. Distant galaxy clusters, observed as they were billions of years ago, appear more tightly packed than their modern counterparts. Filaments in the early universe were denser, richer with gas, and more efficient at funneling matter into galaxies. Today, star formation rates have plummeted to a fraction of their peak, partly because dark energy's expansion has stretched the web's supply lines too thin. In the far future, simulations suggest this trend will only accelerate. Filaments may snap like overstretched wires, isolating galaxies in an ever-growing sea of nothingness. Yet this isn't just a story of slow dissolution. The interplay between dark energy and the cosmic web holds clues to the universe's ultimate fate. If dark energy's strength remains constant, the web will fade but never vanish entirely, its last galaxies clinging to skeletal filaments in a cold, dark cosmos. But if dark energy intensifies over time, a scenario called the Big Rip could tear even atoms apart, unraveling the web completely. Alternatively, if dark energy weakens, gravity might regain the upper hand, allowing the web to persist in some form indefinitely. What makes this cosmic struggle so fascinating isn't just its scale, it's how intimately it connects to our own existence. The same expansion that threatens the web's future also dictated its past. Without dark energy's subtle push in the universe's early moments, matter might have clumped too densely, collapsing into black holes instead of galaxies. The cosmic web exists in its current form because of a delicate balance between these opposing forces, a balance that, for now, has allowed galaxies, stars, and planets to form. As astronomers map the web's evolution across cosmic time, they're not just studying structure, they're reading the universe's destiny written in the language of gravity and expansion. Every observation of distant filaments, every measurement of galaxy motions, adds another piece to the puzzle. And while dark energy may one day erase the web from the sky, for now, it's a reminder that even the largest structures in existence are part of a dynamic, ever-changing cosmos, one where creation and dissolution dance on a scale beyond human comprehension. Quasars are the universe's ultimate searchlights, blazing beacons so powerful they can illuminate the darkest corners of the cosmic web. At their core lies a supermassive black hole, millions to billions of times heavier than our Sun, devouring matter with such ferocity that the infalling gas heats up and glows brighter than an entire galaxy. This isn't just light. It's radiation so intense it strips electrons from atoms, ionizing hydrogen gas for millions of light years around. And that's precisely what makes quasars invaluable. They turn the cosmic web's invisible filaments into glowing roadmaps, revealing structure where our eyes would see only emptiness. Imagine standing in a foggy forest at night, holding a flashlight. The beam cuts through the mist, exposing swirling patterns you'd never see otherwise. Quasars work the same way on a cosmic scale. As their light travels toward Earth, it passes through the web's gas filaments, which absorb specific wavelengths like a chemical fingerprint. By analyzing these absorption lines, especially a telltale feature called the Lyman alpha forest, astronomers can reconstruct the web's architecture in astonishing detail. Some filaments are nearly pristine, bearing only hydrogen and helium from the Big Bang. Others are laced with heavier elements like carbon and oxygen, the recycled remnants of exploded stars. What's truly remarkable is how far back quasars let us see. The most distant ones detected existed when the universe was less than 1 billion years old, yet their light still carries traces of the web's earliest strands. These ancient filaments were denser and hotter than today's, buzzing with the energy of a young cosmos. By comparing them to modern structures, we've watched the web evolve, filaments thinning as the universe expands, voids growing larger, and galaxies migrating toward nodes like commuters drawn to city centers. But quasars don't just light up the web, they shape it. Their radiation acts like cosmic wind, pushing gas away and carving bubbles in the intergalactic medium. In some regions, this creates pressure fronts that trigger star formation. In others, it starves galaxies of fuel. The brightest quasars can even blow entire filaments apart, their energy overwhelming gravity's pull. It's a reminder that the cosmic web isn't static. It's a dynamic battleground where forces vie for control, and quasars are some of its most powerful players. Thanks to telescopes like Hubble and the upcoming James Webb successor, we're mapping these interactions in unprecedented detail. Each quasar we study is like a probe sent into the cosmic depths, its light a messenger carrying secrets from across space and time. And as we decode these signals, we're not just charting the universe's structure, we're uncovering the very rules that govern its growth, from the tiniest gas cloud to the grandest filament. For decades, astronomers faced a cosmic accounting problem where was half the universe's ordinary matter hiding. Stars, planets, and galaxies only added up to about half the expected baryonic matter, the stuff that makes up everything we can see and touch. It was as if the universe had misplaced an entire mountain of material, leaving scientists scratching their heads. The answer, it turns out, was hiding in plain sight, or rather, in the faint, diffuse gas strewn across the cosmic web. This missing matter wasn't truly lost, just incredibly difficult to detect. Picture searching for a whisper in a hurricane. The gas between galaxies is so thin, so spread out, that it barely emits any light. Most telescopes simply couldn't see it, but by studying how this gas absorbs the light of distant quasars, astronomers caught glimpses of its presence. The real breakthrough came with X-ray telescopes like Chandra, which could detect the faint glow of superheated gas trapped in the web's filaments. At temperatures of millions of degrees, this gas doesn't shine invisible light, it radiates X-rays, revealing itself only to instruments designed to peer into the universe's most energetic realms. What they found was astonishing. This warm, hot intergalactic medium, or WIM, contains nearly all the missing baryons, woven into the cosmic web like threads of invisible silk. Some of it is primordial gas, unchanged since the Big Bang, while other regions are laced with heavy elements blasted out by supernova and galactic winds. It's not concentrated in any one place instead. It's spread across vast distances, filling the spaces between galaxies in a tenuous but all-encompassing fog. Mapping this elusive material has required ingenious techniques. One method relies on the Sunyaev-Zeldovich effect, where hot gas distorts the cosmic microwave background as it drifts through galaxy clusters. Another studies the way X-rays from distant sources flicker as they pass through filaments, like headlights dimming in a cosmic haze. Each observation adds another piece to the puzzle, confirming that the universe isn't missing matter after all. It's just been hiding in the last place we thought to look. The implications are profound. This diffuse gas isn't just filling space, it's the reservoir from which galaxies form and grow. When a filament funnels gas into a galaxy, it's tapping into this vast, hidden supply. Over billions of years, the cosmic web's hidden baryons have shaped the evolution of galaxies, determining where stars ignite and where darkness lingers. And as our tools grow sharper, we're finally beginning to see this invisible scaffolding for what it is: not empty space, but the universe's silent scaffolding, holding the answers to questions we've only just begun to ask. The cosmic web we know, with its delicate filaments of galaxies and vast, echoing voids, might not be the only one of its kind. Some theories in physics suggest our entire universe could be just a single thread in an unimaginably larger tapestry, one where countless other cosmic webs exist, each with its own unique rules. Imagine a library where every book contains a different universe, and ours is just one volume on the shelf. In some of these alternate realities, gravity might be stronger, snatching matter into dense clumps with no delicate filaments at all. In others, dark energy could dominate so fiercely that no structures form before expansion tears them apart. There might even be universes where matter behaves in ways we can't fathom, where atoms don't exist or where time flows backward. This idea, known as the Multiverse Theory, isn't science fiction. It emerges naturally from certain interpretations of quantum mechanics and cosmic inflation. When our universe began, space may have expanded so rapidly that pockets of it pinched off into separate realms, each with slightly different physical constants. Think of it like bubbles forming in boiling water. Each one a self-contained universe, some stable like ours, others collapsing instantly or expanding too fast for galaxies to form. The cosmic web we see, then, wouldn't be a universal blueprint, just one possible arrangement among infinite variations. What's fascinating is how this reshapes our understanding of uniqueness. If multiverse theories hold, the delicate balance that allows our cosmic web to exist, the precise strength of gravity, the exact amount of dark energy, might not be special at all. It could simply be the result of chance, one outcome in a cosmic lottery where countless other universes ended up less hospitable. In some, matter might clump too densely, creating a universe of black holes. In others, expansion could outpace gravity entirely, leaving a cold, empty void. Our web of galaxies, in this view, isn't inevitable. It's just one possibility that played out in our particular bubble. Yet for all its speculative allure, the multiverse remains untested. Some scientists argue it's not even science, since we can't observe these other realms directly. But there are indirect ways to probe the idea. If our universe collided with another in the distant past, the shockwave might have left scars in the cosmic microwave background, subtle patterns we could detect with future telescopes. Alternatively, if the laws of physics vary slightly across space, that could hint at a broader multiverse where constants aren't fixed. Even without proof, the multiverse challenges us to think bigger. It turns the cosmic web from a singular marvel into a single stitch in a much grander quilt. And if other webs exist, what structures might they hold? Maybe some have lattice-like grids of galaxies or fractal patterns repeating at every scale. Others could be filled with exotic matter we've never seen, forming shapes beyond our imagination. The possibilities stretch as far as the mind can wander, and perhaps farther still. Whether the multiverse is real or not, the mere idea reshapes our cosmic perspective. It reminds us that the universe we call home, with its intricate web of galaxies, might be far stranger and far less alone than we ever suspected. Among the cosmic web's most elusive inhabitants are neutrinos, ghostly particles so insubstantial they pass through entire planets like moonlight through glass. Born in the hearts of exploding stars, violent black holes, and the Big Bang itself, these nearly massless travelers barrel through the universe at near light speed, indifferent to magnetic fields, gas clouds, or even solid lead. Yet for all their stealth, neutrinos might hold the key to mapping the cosmic web's darkest corners, revealing structures even light cannot touch. What makes neutrinos extraordinary isn't just their ability to slip through matter, it's how they interact with gravity. While light bends around massive objects, creating the warped images we call gravitational lensing, neutrinos experience these distortions too, but with a crucial difference. Unlike photons, which scatter or absorb when they hit gas and dust, neutrinos sail cleanly through the web's densest filaments, carrying undistorted signals from the universe's most crowded regions. Imagine trying to study a city's layout by listening to sound waves bouncing off buildings. Neutrinos would be the whispers that pass straight through walls, bringing you news from hidden alleyways and sealed rooms. This potential hasn't gone unnoticed. Next-generation detectors like the Deep Underground Neutrino Experiment, or DUNE, are being designed to catch these cosmic phantoms in acts of revelation. By analyzing how neutrino paths curve as they pass through galaxy clusters and filaments, scientists could reconstruct the web's mass distribution in 3D, spotlighting dark matter's hidden architecture. It's akin to tracing the outline of a shadow. You can't see the object casting it, but its shape betrays its presence. The real breakthrough would come from combining neutrino data with traditional observations. Picture overlaying a map of light-emitting galaxies with a neutrino-derived map of mass. Discrepancies between the two could expose voids where dark matter lurks without stars, or reveal filaments too faint for telescopes to spot. Even more tantalizing, some neutrinos are ancient, dating back to the universe's first seconds. If we could trace their paths backward, we might glimpse the cosmic web's primordial form, watching gravity's first stitches in the fabric of space-time. Yet capturing neutrinos is like trying to catch smoke with your hands. Current detectors, buried deep underground to shield from interference, register only a fraction of the trillions passing through Earth every second. Future observatories might deploy vast arrays in Antarctic ice or ocean depths, turning entire planets into neutrino telescopes. The payoff: a revolutionary view of the web, not as a static snapshot, but as a dynamic flow chart of matter in motion, a universe seen through the eyes of particles that have witnessed everything from the birth of stars to the tug of voids. For now, neutrinos remain cosmic enigmas, their full potential just beyond our grasp. But as technology advances, these ghostly travelers may become our guides to the invisible, painting the cosmic web in strokes no telescope could replicate. They remind us that sometimes, to see the universe most clearly, we must stop relying on light and learn to read the shadows instead. The universe has a soundtrack, not the eerie silence of space we imagine, but a deep, resonant hum woven into the very fabric of the cosmic web. Picture plucking a guitar string. The vibrations travel through the air as sound waves. Now imagine the early universe, a seething plasma of particles and energy, where gravity and pressure created colossal sound waves that rippled outward like the echoes of a cosmic drum. These waves, frozen in time when the universe cooled, left their imprint on the distribution of matter, a pattern we now see etched into the cosmic web's filaments like grooves on a record. These ancient vibrations are called Baryon acoustic oscillations, or BAO, and they're one of astronomy's most powerful tools. Think of them as the universe's tuning forks, vibrating at precise frequencies that reveal the scale of the cosmos. When astronomers measure the distance between galaxies, they're often tracking these subtle ripples, like finding two notes in a song separated by a perfect fifth, an interval that betrays the size of the instrument. The web's filaments don't just connect galaxies, they sing a harmony written 14 billion years ago, with each BAO acting as a milestone in the expanding universe. What's astonishing is how clear this signal remains. Despite eons of cosmic evolution, the BAO pattern persists, a fossilized echo of the universe's fiery youth. By mapping it, scientists have pinned down the universe's expansion rate with unprecedented precision, uncovering the roles of dark matter and dark energy in shaping space-time. It's as if we've discovered the universe's sheet music, with BAOs marking the tempo and the cosmic web's filaments as the staves. But this isn't just a cosmic curiosity, it's a revelation about how structure emerges. Those primordial sound waves didn't just fade, they seeded the web itself, their peaks and troughs becoming the dense knots and empty voids we see today. The same physics that makes a church organ pipe resonate at a specific pitch also dictated where galaxies would bloom and where darkness would linger. Even now, the universe hums along, its expansion stretching those ancient notes into deeper registers, a bassline so low it's felt more than heard. The next time you gaze at the night sky, remember, you're not just looking at stars. You're witnessing the aftermath of a symphony that began before time had meaning, its melodies written in the positions of galaxies and the spaces between them. And with every new survey, every sharper map of the web, we're learning to listen more closely, tuning our instruments to the universe's oldest song. Galaxies aren't the solitary giants they appear to be. They're voracious predators, growing by devouring their neighbors in a slow-motion feast guided by the cosmic web's invisible hands. Picture the universe's largest galaxies as cosmic whales, swimming through filaments of dark matter and gas, their immense gravity funneling smaller galaxies toward them like krill swept into a tidal current. The Milky Way, our own galactic home, bears the scars of this celestial dining, streams of stars arcing across our halo, the remnants of dwarf galaxies torn apart and absorbed over billions of years. These stellar fossils, like the Sagittarius dwarf spheroidal currently being dismantled by our galaxy's gravity, tell a story of relentless consumption written in the language of motion and light. This process, called galactic cannibalism, isn't random violence, it's gravity's meticulous sculpting. When two galaxies meet along a filament, their dance is choreographed by the web's underlying structure. The larger galaxy's gravity stretches the smaller one into ribbons of stars, a phenomenon astronomers poetically call tidal disruption. Some stars are flung into the void, but most are digested, swelling the predator's size and altering its shape. The Andromeda Galaxy, our nearest spiral neighbor, showcases this beautifully. Its extended halo contains the shredded remains of galaxies it's consumed, a graveyard of cosmic conquest visible only through sensitive telescopes. What makes this cannibalism possible is the web's role as a galactic conveyor belt. Filaments act as highways, guiding smaller galaxies toward dense clusters where giants lurk. Without this directed flow, galaxies might pass like ships in the night, their encounters rare and brief, but the web ensures frequent collisions, especially in nodes where filaments intersect. The Virgo cluster, for instance, is a notorious feeding ground, with massive ellipticals at its core that have grown fat by consuming hundreds of smaller galaxies. Their smooth, featureless shapes betray their violent pasts. Unlike spirals with their delicate arms, these galaxies are the bloated remnants of endless mergers. The aftermath of these feasts reshapes more than just galaxies. As they merge, their central black holes spiral together, eventually colliding in gravitational waves that ripple through space-time. The gas stripped from consumed galaxies ignites bursts of new stars, while the influx of fresh material can awaken dormant black holes, transforming them into brilliant quasars. Even dark matter gets redistributed, altering the gravitational landscape for future mergers. It's a cascade of consequences that began with a filament's gentle tug, proving the web doesn't just connect galaxies, it engineers their evolution. Yet this cannibalism has limits. Galaxies can grow only so large before they exhaust their supply of neighbors, and the universe's accelerating expansion may one day stretch filaments too thin for fresh deliveries. For now, though, the cosmic web remains the universe's grand banquet hall, where galaxies dine on each other in a cycle as old as time itself, a reminder that even the grandest structures are born from countless smaller acts of destruction. The cosmic web, for all its grandeur, is not eternal. The same forces that birthed it will one day transform it beyond recognition or erase it entirely. Dark energy, that mysterious pressure stretching the universe apart, acts like an invisible hand pulling at the threads of this cosmic tapestry. Today, filaments stretch millions of light years, connecting galaxies in a delicate dance. But given enough time, those threads will grow taut, then brittle, until they snap under the strain of relentless expansion. Galaxies now bound together by gravity's embrace will drift apart, their shared history severed as the space between them inflates faster than light can bridge the gap. Imagine looking up at the night sky in 1 trillion years. The constellations we know will have vanished, not because stars died, but because the space between them has stretched so much their light can no longer reach us. Entire galaxy clusters will appear frozen in time, their light redshifted into oblivion. The cosmic web's grand architecture will fade into isolation, its once vibrant nodes reduced to islands in an ever-darkening sea. This is the Big Chill scenario, a slow, cold unraveling where the universe doesn't end with a bang but with a whisper, yet there's a more violent possibility. If dark energy's strength increases over time, it could trigger the Big Rip, a cataclysmic endgame where not just filaments, but galaxies, stars, and even atoms are torn apart. In this scenario, the cosmic web wouldn't just fray, it would shatter. Filaments would snap like overstretched rubber bands, galaxies would disintegrate as their stars are flung into the void, and eventually the fabric of space-time itself would rupture. The universe's final moments would be a cacophony of dissolution, with no structure left to witness its own demise. Clues to our fate hide in the web's current behavior. By measuring how fast filaments are stretching, astronomers can gauge dark energy's grip. Subtle distortions in the web's structure, like the way some voids grow faster than expected, hint at whether expansion will remain steady or accelerate toward catastrophe. Even the Milky Way's motion offers clues. If dark energy's push is stronger than we think, our galaxy's trajectory toward the Great Attractor could one day reverse, as if the universe itself is yanking us backward. But here's the twist: the cosmic web's destruction isn't just a far future abstraction. It's happening now in slow motion. Every second, expansion steals a little more of the web's connective tissue, diluting the density of filaments bit by bit. This gradual unraveling means we're living in a golden age of cosmic connectivity, a fleeting window where the web is still intact enough for us to study it. Future civilizations, if they arise in distant epochs, might gaze at a sky devoid of galaxies, with no clue that a vast network once bound the cosmos together. Whether the universe ends in a whimper or a roar, the cosmic web's fate is a reminder of how temporary even the grandest structures are. Yet its study is more than an exercise in cosmic doom-scrolling. By tracing its evolution, we're piecing together the universe's life story from its fiery birth to its uncertain twilight. And in that story, we're not just observers. We're characters woven into the web's narrative, our existence made possible by the very forces that will one day dissolve it. Einstein's theory of general relativity didn't just revolutionize our understanding of gravity, it gave us the blueprint for the cosmic web itself. Picture spacetime not as a static stage, but as a flexible fabric, warped by the weight of matter like a trampoline sagging under a bowling ball. Where the fabric dips deepest, galaxies gather, drawn together by gravity's invisible tug. This bending of spacetime doesn't just create isolated pits, it weaves an entire landscape of ridges and valleys, with filaments tracing the peaks where matter flows like water down a mountainside, and voids stretching across the lowlands where spacetime curves gently, empty and undisturbed. Yet for all its predictive power, relativity might not have the final word. Astronomers have noticed something peculiar. Galaxies move faster than Einstein's equations say they should, especially at the edges of clusters. It's as if invisible hands are nudging them along, adding speed beyond what the visible matter can explain. This anomaly, known as the missing gravity problem, has sparked a fiery debate. Is dark matter, the unseen scaffolding we've relied on for decades, truly the answer? Or could gravity itself behave differently on cosmic scales, bending the rules we thought were set in stone? Enter modified Newtonian dynamics, a bold alternative that tweaks the laws of gravity to explain these odd motions without invoking dark matter. Imagine gravity weakening less rapidly over distance than Newton or Einstein predicted, like a radio signal that doesn't fade as expected. In this view, filaments and voids aren't shaped by hidden mass but by gravity's own hidden quirks. Some galaxies fit predictions startlingly well, particularly faint, diffuse ones where dark matter's influence should be obvious but isn't. But the cosmic web isn't easily swayed by theory alone. Its structure, the precise way filaments branch, the exact sizes of voids, holds the key to testing these ideas. Supercomputer simulations pit relativity against racing to see which can better recreate the web we observe. So far, dark matter models win at painting the universe's large-scale structure, while struggles to explain why clusters like the bullet cluster show clear signs of invisible mass separating from visible matter during collisions. Yet the discrepancies linger, gnawing at the edges of our understanding. What makes this more than an academic debate is how deeply it cuts to the core of physics. If relativity falters here in the web's vast architecture, it wouldn't just redefine gravity, it would force us to rewrite the story of how the universe builds its grandest structures. Every filament, every void becomes a courtroom where Einstein's legacy is judged, and the verdict could reshape everything from galaxy formation to the fate of the cosmos. For now, the cosmic web remains both a triumph and a taunt. It confirms relativity's brilliance while whispering of secrets still unlearned. As telescopes map deeper and simulations grow sharper, we're not just tracing the web's threads, we're tugging at them, testing which ones hold and which might unravel into something entirely new. Earth's story begins not in isolation, but as part of an interstellar supply chain stretching back billions of years. Every atom in your body, the oxygen in your lungs, the iron in your blood, the calcium in your bones, was once scattered across the cosmic web, riding filaments of gas like leaves floating down a river. Our solar system didn't form from nothing. It condensed from a dense knot in this vast network where gravity gathered material delivered across cosmic distances. The very hydrogen fueling our sun, its primordial cargo, traveling untouched since the Big Bang until the Webb's currents deposited it here, in this unremarkable corner of a spiral galaxy. The heavier elements tell an even more dramatic tale. Carbon, nitrogen, oxygen, the building blocks of life, weren't forged in our neighborhood. They were born in the hearts of massive stars that lived fast and died violently, their explosive deaths scattering these precious ingredients across interstellar space. Supernova shockwaves, like cosmic conveyor belts, pushed these elements into the Webb's filaments, where they mixed with other gas flows over millions of years. Gold from colliding neutron stars, uranium from rare stellar cataclysms, all hitched rides on these intergalactic highways before eventually reaching the molecular cloud that birthed our solar system. What makes this delivery system so remarkable is its precision. Too much heavy element enrichment, and planetary systems might form with toxic abundance. Too little and rocky planets like Earth might never coalesce. The Webb didn't just bring materials, it delivered them in the right proportions at the right time to a quiet suburb of the Milky Way where conditions were perfect for life to eventually emerge. Even Jupiter's placement as a cosmic shield, deflecting comets that later brought water to Earth, traces back to how the Webb's structure influenced our solar system's formation. This interconnectedness extends beyond our origins. Right now, the same processes that built our world are unfolding elsewhere in the cosmos. In the Orion Nebula, new solar systems condense from Webb-fed gas clouds, some perhaps receiving the same life-bearing elements we did. The TRAPPIST-1 system's 7 Earth-sized worlds, they owe their existence to filaments that channeled material to their birth cluster billions of years ago. Even rogue planets cast adrift from their stars still carry the chemical fingerprints of their Webb-born beginnings as they drift through interstellar darkness. The ultimate marvel is that we've become the Webb's consciousness, a way for the universe to understand itself. The carbon in your DNA, the iron in your blood, the phosphorus in your bones, all were once scattered across light years, now assembled into a form that can trace its own cosmic lineage. When astronomers map the Webb's filaments or when a child gazes wonderingly at the stars, we're not just observing the universe, we're the universe observing itself, the end product of a delivery system older than time, finally awake to wonder how it all came to be. Artificial intelligence is quietly revolutionizing our hunt for the cosmic web, not by replacing astronomers, but by becoming their most powerful collaborator. Picture a cosmic game of connect the dots where the dots number in billions and the connections span millions of light years. That's the challenge AI faces as it sifts through terabytes of telescope data, spotting faint galactic patterns with superhuman precision. Unlike human eyes that might glaze over repetitive structures, machine learning algorithms thrive on pattern recognition, teasing out filamentary connections in galaxy surveys that would take lifetimes to map manually. The breakthrough lies in how these systems learn. Trained on both real observations and hyper-realistic universe simulations, AIs develop an almost intuitive grasp of cosmic web geometry. They can predict where filaments should thread through unexplored regions of space based on surrounding galaxy positions, like a chef anticipating how melted chocolate will spread across a tilted plate. Some algorithms have even rediscovered known filaments independently, validating their methods while uncovering previously overlooked strands. The Dark Energy Surveys AI, for instance, recently identified a filament bridging the Coma and Leo galaxy clusters, a structure spanning 60 million light-years that had eluded human detection for decades. What makes this partnership so transformative is speed. Where traditional analysis might take months to map a single filament, AI can process entire sky surveys in days, flagging thousands of potential web structures for closer study. The upcoming Vera Rubin Observatory will generate more data every night than the Hubble Space Telescope collected in 30 years, an avalanche of information only machine learning can realistically pass. These systems don't just find needles in cosmic haystacks, they rebuild the entire haystack's blueprint, revealing how each strand connects. Yet the most exciting frontier is predictive modeling. Advanced neural networks now simulate how filaments evolve over billions of years, testing theories about dark matter's role and dark energy's influence with unprecedented granularity. Some models suggest certain filament configurations could harbor galaxy highways, regions where gas flows so efficiently they produce exceptionally bright galactic clusters. Others hint that the web's finest threads might glow faintly with unexplored particle interactions. These digital probes allow astronomers to test ideas before committing precious telescope time, turning AI into a virtual universe where hypotheses can be safely stress-tested. The synergy between silicon and scientist is reshaping cosmic exploration. When humans and machines combine their strengths, our curiosity and creativity with their speed and pattern recognition, we're not just mapping the cosmic web. We're learning to speak its language, uncovering rules of cosmic architecture that govern everything from galaxy formation to the universe's ultimate fate. And as AI grows more sophisticated, it may soon ask its own questions about the web's mysteries, guiding telescopes toward discoveries we haven't even thought to pursue. Long before telescopes pierced the heavens, humanity's storytellers wove tales of a connected cosmos, visions that now seem almost prophetic. The Norse imagined Yggdrasil, a colossal ash tree whose roots and branches linked the 9 realms, while Hindu sages spoke of Indra's net, an infinite web of jewels where every reflection contained all others. The Maya saw the Milky Way as the world tree, its roots in the underworld and branches cradling the stars. These myths, separated by continents and centuries, share an uncanny thread: the idea that the universe is bound together by invisible strands, a tapestry of interdependence modern science has only just begun to map. What's startling isn't just the similarity of these stories, it's their precision. Indigenous Australian Dreamtime legends describe the song lines, pathways crisscrossing the land and sky, mirroring the way galaxies trace filaments of dark matter. The ancient Greeks envisioned the moirai, the 3 fates, spinning and cutting the threads of destiny, a metaphor that now feels eerily close to the cosmic web's delicate balance of creation and dissolution. Even the Cherokee spoke of a great spider weaving the world into existence, her silk threads echoing the filaments where galaxies now cluster. These weren't just poetic flourishes, they were intuitive grasps of a truth it would take millennia to confirm: that emptiness is an illusion and connection is the universe's deepest law. Science has since replaced myth with measurement, but the parallels remain profound. Where storytellers saw the world tree's branches, we now map galaxy superclusters strung along filaments. The jewels of Indra's net find their counterpart in the way every particle in the web influences every other through gravity's invisible pull. Even the concept of cosmic recycling, central to myths from ancient Egypt to the Andes, aligns with modern astrophysics, as gas flows along filaments to birth new stars while supernovae scatter heavy elements back into the web. The old stories got the scale wrong, but the architecture startlingly right. This convergence raises a tantalizing question: how did cultures with no telescopes intuit structures we've only confirmed in the last few decades? Some scholars suggest it's a case of pattern recognition, the human mind instinctively seeking connections, whether in star lore or spiderwebs. Others point to shamanic traditions involving altered states, where visions of luminous networks might have mirrored the brain's own neural architecture, externalized as cosmic maps. But perhaps the simplest explanation is that the universe leaves clues everywhere. The branching of rivers, the veins of leaves, the mycelial networks beneath forests, all echo the web's fractal beauty, offering nature's own hints at a deeper order. Today, as supercomputers simulate the web's evolution and telescopes trace its faint glow, we're fulfilling an ancient human impulse to chart the unseen threads that bind us to the stars. The difference is that now, when we speak of cosmic connections, we can point to the delicate tendrils of gas spanning the Abel cluster or the precise gravity calculations proving two galaxies are linked. Yet in our awe, we're not so far from the storytellers who sat beneath the stars millennia ago, spinning tales of woven heavens. They may have called it destiny or divinity, where we call it dark matter and dynamics, but both visions share a truth too profound to be coincidence. The universe really is a web, and every myth that ever hinted at it was a single thread in humanity's grand, unfolding understanding. Time sculpts the cosmic web as surely as gravity shapes its form. Each filament, each void, carries a timestamp written in the motion of galaxies and the stretching of space. When we peer at distant objects like the spiderweb galaxy, we aren't just seeing faraway light, we're stepping into a time machine. That faint glow traveled billions of years to reach us, showing the web in its adolescence, a period when filaments were thicker, gas was richer, and galaxies collided with reckless abandon. Compare this to our local universe, where filaments have stretched thinner and voids have ballooned, and you witness the web's grand evolution unfolding frame by frame. The difference between then and now is staggering. In the early universe, filaments blazed with heat, ionized by the furious energy of young quasars and supernova. Gas streamed along these channels at breakneck speeds, fueling galaxies so prodigious they birthed stars hundreds of times faster than the Milky Way does today. Now, those same filaments have cooled and diluted, their once roaring currents slowed to a trickle by the universe's expansion. Voids, once modest gaps, have grown into yawning chasms, some so vast they distort our view of the cosmic microwave background, their emptiness bending light like a funhouse mirror. This transformation isn't random, it follows a rhythm dictated by dark energies' growing dominance. Early on, gravity ruled unchallenged, pulling matter into dense knots and braiding filaments tighter. But as dark energies' push intensified, it began stretching the web's threads like taffy, forcing galaxies to drift apart. Astronomers track this shift by measuring redshift, the stretching of light's wavelength as space expands. The farther back we look, the more redshifted the light, and the younger and denser the web appears. It's how we know the universe wasn't always this sparse, this orderly. It began in chaos, and the cosmic web is its slow, elegant unraveling. Yet the web's life cycle holds even deeper clues. Some filaments, observed in the distant past, appear fragmented evidence of violent encounters where galaxy clusters ripped through them like bullets through gauze. Others show signs of filament mergers, where two strands intertwine to form a superhighway, funneling galaxies into colossal hubs. These events aren't just history, they're the universe's way of recycling, of repurposing old structures into new. Even our Milky Way may owe its spiral arms to an ancient filament collision, a long-ago encounter that stirred its gas into graceful swirls. The web's fate hinges on a tug-of-war between memory and oblivion. Gravity struggles to maintain its structure, while dark energy pulls the threads ever thinner. In the far future, the space between galaxies will stretch so much that today's web will seem like a fleeting moment, a brief, shining network in an otherwise disconnected cosmos. But for now, we live in the web's golden age, where its patterns are still sharp enough to read, its history still vivid enough to trace. Every distant galaxy we observe is a stitch in time, connecting us to the universe's fiery youth and to the slow, inevitable drift toward whatever comes next. Black holes aren't cosmic accidents, they're inevitable products of the universe's architecture, born where the cosmic web's filaments knot together in gravitational handshakes. Picture the web's densest intersections as whirlpools in a cosmic river, where gas flowing along filaments spirals inward, compressing until space-time itself collapses. These aren't just any black holes, they're supermassive beasts millions to billions of times heavier than our Sun, lurking at the hearts of galaxies like spiders at the center of a web. The Milky Way's own Sagittarius, a star with its 4 million solar mass appetite, is a modest example. Some galactic cores harbor black holes so immense they outshine their host galaxies when feeding. What makes these monsters so revealing is how they trace the web's hidden currents. Just as trees grow tallest where soil and water are richest, supermassive black holes balloon to staggering sizes where filaments converge, gorging on the gas these cosmic pipelines deliver. The Phoenix Cluster's central black hole, for instance, sits where a dozen filaments meet, its appetite sustained by a non-stop buffet of intergalactic matter. Telescopes have caught these behemoths in the act, their accretion disks glowing brighter than entire galaxies as they shred gas clouds into swirling plasma. The energy released is unimaginable. A single feeding black hole can outshine every star in its galaxy combined, heating surrounding gas to millions of degrees and carving cavities in the cosmic web itself. But black holes don't just consume, they shape the web around them. Their ferocious winds and jets, powered by magnetic fields twisted to breaking point, blast gas back into the filaments like cosmic fire hoses. This feedback loop is crucial. Too much gas flowing in and stars form uncontrollably. Too little and galaxies starve. The web's finest filaments often glow at their tips with the telltale X-ray signature of black hole winds, evidence of these gravity-powered regulators at work. In the early universe, quasars, supermassive black holes in their most violent phase, likely pumped energy into the web's gas, preventing it from collapsing into galaxies too soon. Without this balancing act, the cosmos might have burned through its star-forming fuel before life could emerge. The most fascinating black holes are those caught mid-meal. In galaxy cluster Abell 2587, astronomers spotted a supermassive black hole that had strayed from its galactic center, trailing a 50,000 light-year long tail of newborn stars. The explanation: it was drifting along a filament, consuming gas so rich that the leftovers ignited star formation in its wake. Other black holes, like the one in galaxy SDSS J1, 126+0145, show spiral patterned accretion disks, direct evidence of gas spiraling in along a filament's twisted magnetic field lines. These observations confirm what simulations suggest. Black holes don't grow randomly, but along the web's predefined highways. Yet for all their violence, black holes may be the web's ultimate recyclers. The elements forged in their accretion disks, gold, platinum, uranium, get flung back into the filaments by their jets, enriching future generations of stars and planets. The iron in your blood, the calcium in your bones, might have once cycled through such a cosmic forge. Even their gravitational waves, rippling outward from collisions, could stir the web's gas, triggering new star formation like a pebble dropped in a pond. As instruments like the Event Horizon Telescope and the upcoming LISA gravitational wave detector peer deeper, we're not just studying black holes, we're using them as probes to map the web's densest recesses. Their growth rates, their positions, even their spin directions all encode information about the filaments that feed them. In this light, every supermassive black hole becomes a cosmic signpost, pointing the way to the universe's hidden scaffolding. and to the forces that have shaped everything from the largest galaxy clusters to the atoms in our bodies. The cosmic web doesn't belong to astronomers alone. It's a puzzle waiting to be pieced together by curious minds everywhere. Projects like Galaxies have turned galaxy classification into a global collaboration, where teachers, artists, and even schoolchildren help trace the web's intricate patterns. Imagine logging onto your laptop after dinner and spending an hour clicking through images of distant galaxies, your simple categorizations contributing to papers published in top scientific journals. This isn't hypothetical, it's happening right now. Over the past decade, volunteers have classified millions of galaxies, uncovering rare structures like red spirals and green peas, discoveries that automated algorithms missed because the human eye spots anomalies machines don't. What makes these efforts so powerful is their scale. No research team, no matter how well funded, could manually inspect the billions of galaxies captured by telescopes like Hubble or the Sloan Digital Sky Survey. But distribute that task to hundreds of thousands of volunteers, and suddenly the cosmic web's map gains unprecedented detail. In 2014, Dutch schoolteacher Hanny van Arkel stumbled upon a celestial oddity while classifying galaxies, a mysterious green blob now known as Hanny's Voorwerp, a glowing cloud of gas illuminated by a long-dead quasar. Her discovery, made from her living room, reshaped our understanding of how black holes interact with their surroundings. The beauty of citizen science lies in its democratization of discovery. You don't need a PhD to recognize that a galaxy looks like a whirlpool or a football. Platforms like Zooniverse have expanded beyond galaxy classification, inviting the public to track gas flows in filaments, identify gravitational lenses, and even hunt for distant quasars. Each click adds another data point to our collective understanding, proving that the cosmic web isn't just something we observe, it's something we explore together. When a retiree in Tokyo flags a peculiar galaxy cluster or a teenager in Buenos Aires spots a faint filament, they're not just assisting scientists, they're joining a tradition as old as humanity itself, the act of looking up and wondering. This collaborative spirit is rewriting how science gets done. Professional astronomers now routinely incorporate citizen-generated data into their research, using it to train AI systems or verify hard-to-interpret observations. The result, projects that once took years now unfold in months, with discoveries flowing faster than peer review can keep up. And it's not just about speed, crowdsourcing brings fresh perspectives. A graphic designer might notice an artistic symmetry in galaxy arrangements that a physicist overlooks, sparking new questions about the web's formation. Yet the true impact goes beyond data. Every time someone classifies a galaxy, they're forging a personal connection to the cosmos. That spiral you labeled today might become part of a study revealing how filaments channel gas into star-forming regions. The odd-looking elliptical you flagged could help trace dark matter's distribution. These projects remind us that the universe isn't a distant abstraction, it's a living network, and we're all nodes in the web of its exploration. As telescopes grow more powerful, flooding servers with petabytes of data, the role of citizen scientists will only expand. Future missions like the Vera Rubin Observatory will image the entire visible sky every few nights, capturing changes no single team could ever analyze alone. The next great cosmic web discovery might come from a night shift worker in Oslo, a farmer in Kenya, or a student in Mumbai, anyone with curiosity and an internet connection. Because mapping the universe isn't just about technology or expertise. It's about collective attention, the simple act of noticing, and the shared recognition that the cosmos belongs to everyone willing to look. The cosmic web rewrites the story of our universe, transforming what once seemed like a vast and lonely void into a dynamic network pulsing with matter, energy, and unanswered questions. Every filament of dark matter, every glowing strand of gas, every galaxy cluster perched at an intersection, they're all threads in a tapestry so immense it defies comprehension. This isn't just structure, it's the universe's circulatory system, channeling the raw materials for stars, planets, and even life itself across billions of light years. The atoms in your hands, the iron in your blood, the oxygen in your lungs, they all journeyed through this web, riding cosmic currents long before Earth existed. But the web's true power lies in the mysteries it still guards. Dark matter's ghostly embrace, dark energy's relentless push, the possibility of other universes with their own tangled networks. Each unanswered question is a doorway to revelations that could redefine reality. Telescopes like James Webb and the upcoming Nancy Grace Roman Space Telescope are poised to peel back another layer, probing filaments so faint they're barely more than whispers in the dark. Will we find galaxies younger than we thought possible, clinging to threads of primordial gas, or evidence of forces we've yet to imagine, bending the web into shapes that defy our models? What's certain is this: the cosmic web is more than a scientific concept. It's a mirror reflecting our own insatiable curiosity, our need to find connection in the chaos. For centuries, we saw the universe as a scattering of isolated stars. Now we know better. Galaxies aren't strangers drifting apart. They're neighbors linked by invisible highways, their fates intertwined by gravity's unbreakable bonds. Even the emptiness of voids plays its part, shaping the web's flow like the negative space in a sculptor's masterpiece. As we stand on the brink of new discoveries, the web invites us to rethink not just the cosmos, but our place within it. Every observation, every simulation, every volunteer classifying galaxies from their living room adds another stitch to humanity's understanding. So the next time you look up at the night sky, remember, you're not just staring into darkness. You're gazing at a living network, one that cradles galaxies, nurtures stars, and perhaps, in ways we're only beginning to grasp, made our existence possible. The universe isn't empty, it's alive with connection, and the most thrilling part, we're just getting started. What do you think the cosmic web's next revelation will be? Drop your thoughts below. The conversation is as infinite as the web itself.